A wave of molasses came down a Boston street and killed 21 people. It was the 15th of January, 1919. The man who ordered the tank built could not read a blueprint. And no law in Boston said that he had to. The tank had stood on Commercial Street since 1915. Before anyone trusted it with 2.5 million gallons, it was tested once. The man in charge put 6 inches of water in it. 6 inches in a tank 50 feet tall. So this is not a story about a freak accident. It is the story of a steel wall that was about half as thick as it needed to be, and of the 3.5 years it spent saying so out loud. Molasses is sugar, and sugar ferments into alcohol. In 1915, alcohol was not mainly something people drank. It was something armies needed. Industrial alcohol went into smokeless powder and into the filling of shells, and a country at war needs a great deal of it. United States Industrial Alcohol built the tank to hold the raw material. It was 50 feet tall and 90 feet across. Picture a steel drum as high as a 5-story building and wider than it is tall, with houses along one side of it. Full, it was designed to take 2.5 million gallons. Ships came up from the Caribbean and pumped their cargo straight into it. By January 1919, the war had been over for 2 months, but there was a second deadline coming. Prohibition was about to make drinking alcohol illegal, and the company wanted every gallon converted before that market closed. So the tank was kept full. Prohibition was ratified on the 16th of January, 1919. The tank burst on the 15th. It was full for one more day. Arthur Gell was the treasurer of the company. He was an accountant. He had no training in engineering or in architecture. He could not read a technical drawing, and when he was asked in court what a factor of safety was, he did not know. Gell was the man who ordered the tank. He chose the site, approved the plans, and signed for the steel. He did not hire an engineer to check any of it, and he was not required to. In Boston in 1915, a drawing for a structure like this did not have to be signed by anybody at all. The steel arrived as rings of curved plate, stacked one on top of the next and riveted together. The plates were between 1/2 inch and 5/8 of an inch thick. Whether that was enough is a question with a number for an answer, and nobody ever worked it out. There is a proper version of that test. You fill the tank to the top with water, and you leave it there, and you walk around it looking for the places it weeps. You use water because if the tank does let go, what you have spilled is water. A full tank of water is not quite as heavy as a full tank of molasses, but it is close, and it is far more than enough to find a wall that is only half as thick as it should be. It is slow. It costs money. The ships were already coming. 6 inches of water puts less than 1% of that load on the bottom ring. Less than 1%. The test could not have failed, and it could not have told him anything at all. A tank that has never been full has never been tested. From the first filling, it leaked, and not as a drip. Molasses ran down the outside and pooled at the base, and people from the neighborhood came with pails and cans and carried it home. Inside the company, a man named Isaac Gonzalez kept saying so. He watched flakes of rust fall off the shell, picked them up, and put them on Gell's desk. By the summer of 1918, he was waking in the night and walking down to look at the tank. The company did respond to the leaking. It had the seams recaulked at least twice. A structural warning was answered with sealant. Then, in August 1918, the tank was painted. The color they chose was brown. Molasses stains steel brown, so a brown tank does not show a leak. Isaac Gonzalez resigned the next month. The tank burst 4 months after he left. A tank does not hold liquid the way a floor holds weight. It holds it the way a barrel hoop holds staves from around the outside. The molasses presses outward in every direction, and the wall has to resist being pulled apart around its circumference. Engineers call that hoop stress. Two things make it worse. A wider tank means more pull for the same depth, and this one was 90 feet across. And deeper liquid means more pressure, because pressure grows with the height of everything standing above it. At the bottom of 50 feet of molasses, every square inch of the wall is being pushed outward with about 30 pounds of force. That is roughly the pressure in a car tire, applied to every square inch of a wall 90 feet across. Near the top of the same wall, it is almost nothing. So the wall near the top of a tank is barely loaded, and the wall at the very bottom carries almost all of it. That is why the rings get thinner as they go up. The bottom ring does the work. On Commercial Street, the bottom ring was 5/8 of an inch at best, and it needed about an inch. The most heavily loaded part of the structure was the part that was furthest short. When engineers design something that can hurt people, they do not build it to survive exactly the load they expect. They build it to survive several times that load. That ratio is the factor of safety, and it exists because the world never matches the drawing. Steel varies. Rivets vary. Somebody fills it fuller than the plan allowed. In 2014, an engineer named Ronald Mayville rebuilt this tank inside a computer and loaded it. The steel around one rivet hole near the base was carrying more than 16,000 pounds of tension on every square inch. Not 16,000 pounds spread over the wall. 16,000 on every square inch of it. Concentrated at a hole that had been punched rather than drilled. That was past what the standards of 1913 allowed, the rules that already existed 6 years before anyone poured molasses into it. Here the case against Arthur Gel gets complicated. Steel is not equally strong at every temperature. Warm steel bends before it breaks. You get a bulge, a tear, a leak. You get a warning. Cold steel of the wrong kind does not bend. It snaps all at once. The temperature where a steel stops bending and starts snapping is called its ductile to brittle transition. Where that point sits depends on what the steel is made of, and this steel was low in manganese, which pushes the point upward. On the 15th of January, the air in Boston was about 40 degrees. 40 degrees is a mild afternoon in Boston. It was not a mild afternoon for the steel. This steel was at or below its transition, and it had been on every cold day for 3.5 years. That is not what made the 15th different. It meant that when the wall did go, it would not bulge or tear or weep. It would shatter. Nobody in 1915 could have known that. The transition was not understood for another 25 years, and the world learned it from welded ships that cracked in half in cold water. So Gel is not guilty of ignoring the metallurgy. Nobody was doing the metallurgy. And he did not need it. The tank failed on the numbers that already existed in 1913. It did not fail a modern test. It failed the engineering of its own time. He is not guilty of missing what nobody knew. He is guilty of never once having to ask. In the day or two before, a ship had emptied its cargo into the tank. Molasses is stiff when it is cold, so it is warmed before it is pumped. That warm load went in on top of a tank that was already nearly full of cold molasses, sitting through a Boston January. Then the weather turned. The days before the 15th were bitterly cold, and on the 15th it came up to about 40 degrees. Warm molasses ferments faster, and fermenting molasses makes gas, and gas in a closed tank is pressure. It is tempting to make that the cause. It was not. The tank was already carrying more than its steel was allowed to carry with nothing added at all. The gas, if it was there, was the last few pounds on a wall that had been overloaded since the day it was filled. At about 12:30, People nearby heard a sound they later described as a machine gun. That was the rivets. The failure began at a rivet hole beside a manhole in the bottom ring, the most heavily loaded steel in the structure, with a hole punched straight through it. A punched hole is not a clean hole. It leaves a ragged edge, and stress crowds into it. The bottom ring opened. The plates peeled outward, which is what a tank does when the pressure is on the inside, and 2.3 million gallons left it at once. Molasses is about 40% heavier than water, so that is something like 13,000 tons, call it 8,000 cars. A physical model built in 2016 puts the wave at about 25 feet as it came out, which is 2.5 stories and roughly 160 feet across. People at the time said it crossed Commercial Street at about 35 miles an hour, and that model says they were right. A wave of water that size would have knocked people down and run past them. This did not run past. That is the same model. Researchers at Harvard built the Commercial Street waterfront at small scale and poured cold corn syrup through it. What they found is the reason the number is 21. Molasses is only runny while it is warm. Coming out of the tank, it moved like water. Then it met January air and January ground. As it cooled, it thickened, in the middle of its own surge, and went from something like a liquid to something closer to setting cement while it was still moving. People were not swept away. They were caught and then held. Rescuers could not pull them free. It took down a support column of the elevated railway on Commercial Street on its way through. 21 people died and about 150 were hurt. Most of the dead did not work for the company. They were laborers and drivers from the city paving yard and the wharf, stopped for lunch, and they ranged from children to men in their 70s. One of them was a wagon driver named Cesare Nicolo. The wave took him into the harbor, and he was not found for 4 months. The company's defense was that anarchists had blown the tank up. In 1919, that was not an absurd thing to say. There were real bombings that year, and the claim had to be taken seriously. It failed on the metal. When a bomb goes off inside a tank, it opens the wall in one place and leaves burn and blast damage around it. When a tank is simply overloaded, it splits from the bottom and the plates peel outward all the way around. There was no blast damage on the recovered steel. The plates had peeled. More than 100 families and businesses sued, and the cases were joined into one. It ran for 6 years in front of a court-appointed auditor named Hugh Ogden. Around 3,000 witnesses gave evidence, and the transcript came to about 45,000 pages. All of that happened because the company would not concede the one thing the steel on the ground already said. In April 1925, Ogden found the company responsible. It paid $628,000, which is something like $10 million today. Ogden's finding did something a settlement usually does not. It changed what a drawing is. After the flood, Boston required that plans for a structure like this be signed by a licensed engineer, with the calculations handed in beside them. Massachusetts brought in formal licensing. Other states were already moving that way, and this case is one of the reasons they moved faster. That is what the stamp on an engineering drawing is for. It is a name. It means a person with a license has checked the numbers and can be held to them. In 1915, no name was required. A treasurer who could not read a drawing ordered a 50-foot tank, tested it with 6 inches of water, painted it brown when it leaked, and kept it full to the last legal day. Every one of those things was allowed. Like it, subscribe, and you will know when the next one goes up, the thing that held or the thing that did not.